In this video, we're going to take a look at compression and the idea of lossy, lossless and Huffman coding. In this short video, the learning objectives are to explain the need for compression, to understand that data can be compressed in different ways, explain how data can be compressed with Huffman coding, and to represent data in R or E frequency data pairs, and we'll come on to that shortly. So what is compression? We can think of it as reducing the file size while retaining core information. What we essentially mean is that we actually just want fewer bits, and these are just needed to convey that original information. Storage and upload and download of that file can be significantly reduced. Now, there's two that we need to be aware of for the exam. Lossy. Some of the data is removed from the file. It's not used where the data is important for, say, code or a document, but where actually the consequence is that loss of quality. So an image, for example, or a video. After a file is decompressed, the file isn't the same as the original. And JPEG and MP3 are two lossy compression algorithms that are used in the wider world. They partly work by removing sounds and colours we recognise the least. So, on the flip side of that, you've got lossless. No data is essentially removed, but it's rearranged to become more efficient. You can always think of lossy as being a bit more effective as a a compression technique. Let's not be confused about those two. This can be done using run length encoding. What essentially happens is this replaces the repeated data, otherwise known as runs, with frequency or data pairs. So take this as an example. Here I've got 3 yellow, 1 blue, 4 purple and 1 blue. When I run lossless compression, that turns into 4 yellow, 1 blue, 4 purple, 1 blue. It's essentially telling us the frequency that they appear, and it's paired them together in terms of the data that they hold, in this case, data values. We could do this with binary numbers as well, so here's another example. And when I run length encoding, it turns into 5 zeros, 4 ones and another 0. This works best with data that's less likely to have a lot of repeats. And as there's few repeats, for example when you random text, run length encoding may add to the file size. The longer the run, then there's more compression. This is where Huffman coding comes in. It's a method of lossless compression, and it's based on the fact that some data is used more frequently. So for example, here, green is more used than purple or pink. Using a standard representation, we could say that each of them are given the same number of bits. And essentially, Huffman coding instead assigns variable length codes. The more frequent that character is, the shorter the Huffman code is. The algorithm works best by creating a Huffman tree that needs to be stored alongside the compressed data. Let's take a look at how that works. The algorithm states a few simple and fairly straightforward steps. We can think of the word Huffman, and in this case I could think of the amount of times a letter appears in that sequence. Here, Human appears once, whereas F appears twice. We can then create a node for each of those characters and label it with its frequency. We can arrange those nodes in ascending frequency, and take the first two nodes, join them together with the new parent node's label being combined with the frequency of the two nodes. I can then insert that node within the child in the ordered list. We then keep repeating steps 3 and 4 until there's a root node. So let's see that in action. If I'm taking Huffman and the letters that appear in the frequency, I can create a node for each letter. Here are those characters with their frequency. So we can see that I have represented each of the letters along with their frequency in brackets. I can arrange them in ascending order. So in this case, H, U, M, N, and A, and F as 2. And by ascending I mean how many times they repeat. So 1s go first and our 2s. What we then want to do is we want to take the first 2 nodes and join them together, with the new parent node's label being combined with the frequency of the 2 nodes. So in this case, I know that H and U were next to each other. So I'm going to take them here and I'm going to combine them as 2. M, N, A and F remain, and I'm going to put them back into the ordered list. This shows up as M, N, A, F and 2, with our new joint combined frequency at the end of the list. We keep going with steps 3 and 4 until there's a root node. So I'm going to repeat the same for M and N, add them onto the list. If I rejoin them together, I form AF2 and another 2. I could do the same thing again with my A and F, which have different repeated frequencies. I can keep going. If I rejoin them again, I get a much bigger list. Again, I'm going to keep going, and in this case I can simplify it down to where I've got my 2's going to the 4 and my 3's on the side there. When they're rejoined, it looks a bit like this, where the top, or my root node, is a 7. And I've gained that because I've added 3 and 4 together to give me 7. You can see it at each of those nodes. The original letters for the word Huffman are there, with the frequencies all adding to the total number of letters or characters that appear in that sequence. There you go. So the top node should always equal the total number of the original characters. There you go. And in this case, I can label each of them 1s and 0s. Label each of the left rows as a 0, each of the rights as 1, and you keep going from the start at the top and trace to each character, reading off 1s and 0s as you go. Those codes allow you to find each of the characters. Huffman codes are specific to the text and the algorithm implementation as a whole. So the text in this circumstance will be encoded as that binary string. The computer knows when the code for the binary is finished by traversing the tree using a string until a character is reached. Here we go, as an example in hex. We can ignore the additional storage for the tree. The number of bits saved by the compression is 49 minus 18, which is 31B. The more skewed it is, in essence, the more repeats, the better the compression has taken place. Here's some key points about what you have learned by watching this video. You've learned that compression is all about reducing its file size. Lossless compression relatively removes some of the data from the file. The more effective lossy compressions only remove data that is unnoticeable to the human eye. Lossless compression can rearrange data to make it more efficient, and run length encoding collapses repeats into data frequency pairs. Huffman coding is lossless compression and produces variable length codes that the data is repeated most and individually takes up the least space. Hope you found this video useful.